Introduction, and thank you for having me today. Here this week. It's been such a pleasure to hear all these amazing talks and interact with you all. I want to come back to this question of what are exoplanets made of, and at the end I will have a question for you about how do we link that to how they formed. And we already heard from Lauren this morning that we can get some clues about what planets are made of based on their masses and radii that we can measure. For example, things that are kind of big, we know that they need some hydrogen, helium-rich atmosphere to explain that large radius. We have a bunch of exoplanets that are consistent with an Earth-like bulk density, Earth-like composition, so it's fairly reasonable to assume that those are rocky planets. But there's a lot of degeneracy in this space as well, especially kind of in the middle regions where this part that I've shaded in blue, these are planets where we think that they could have a really thin hydrogen-rich atmosphere maybe, or maybe they're slightly underdense because they're enhanced in volatiles like water and carbon. There could also be something interesting going on with their cores. For example, they might not precipitate an iron core like the Earth did. And it's really difficult to disentangle these different effects based only on mass and radius. So we need a bit more information. And one way that we can get that, and a bit of compositional information, is through the atmosphere. But I want to start off with a bit of a warning, I guess, which is that when we're thinking about what a planet's made of, what we really want to know is what is the bulk of the planet made of. That's what we would probably like to link to planet formation models. But when we look at the atmosphere, we're looking at the atmosphere right at the top. And to learn more about the deeper planet, that involves some kind of extrapolation with models, and we need to be careful about how we treat the interaction between the atmosphere and interior. And that's something that I'm going to come back to a little bit later on. But for now, I want to just spend a little bit of time talking about how we do the atmospheric observations. I'm going to attempt to do a really short and really incomplete summary of some of the things that we can do with JWST. So to begin with, the technique that we probably use the most to observe transiting exoplanet atmospheres is transmission spectroscopy. And that's because we're effectively looking for modulations in the stellar light, so that's a nice big signal. And transmission spectroscopy is pretty sensitive to the chemical composition of the atmosphere. I'll get onto flat spectra later. So here, this is an example of WASP39b, and we can see a nice CO2 feature, and a little bump from SO2 as well, which was the first time that SO2 was found in an exoplanet atmosphere. So that's really exciting, and several planets, many planets even, have been observed in that way. But there are other ways that we can look at these atmospheres, and one of my favorites is secondary eclipse spectroscopy, looking at the thermal emission from the planet itself. This is a technique that hasn't been used as much as transmission spectroscopy because it's a little bit more challenging. We're looking at flux coming from the planet, really, rather than the star, and naturally there is less of that flux. So the signal-to-noise tends to be a little bit worse, but if you can get good enough signal-to-noise for certain targets, what we get out of a secondary eclipse spectrum is a lot of thermal information. We're measuring those photons directly from the planet. And in some cases, you can get compositional information. For example, this is the ultra-hot Jupiter WASP-18b, and you can see here these lovely water emission bumps. These look quite nicely defined with HST. This looked flat. We couldn't see those features. And then JWST, it suddenly popped out, and we were all very excited. So secondary eclipse is something I'll come back to, but it's very exciting. We can also take it one step further, and instead of measuring the thermal emission only of the day side of the planet, we can measure it the whole way around the whole orbit and get a phase curve. And what we get with a phase curve is not only the day side emission, but the night side emission, the emission from the planet at other phases as well. And we can really get this sort of 3D view of the planet. And you actually get a transmission spectrum for free as part of that as well. So the keen-eyed of you may have noticed that these are all giant planets. And they're actually all from the JWST Transiting Planet Early Release Science Program. So these were chosen to be very nice, pretty targets that will give us a nice signal. But what about small planets? I want to start off by being more optimistic before I get onto flat spectra. So I want to show some really nice results, just a small selection. Someone mentioned yesterday 2I's 270D, which is a sub-Neptune, where there are visible features in its transmission spectrum of methane, a bit of CO2, some hints of water. So yeah, this is a smaller planet, and yet we can see these molecular features, which is really exciting. Going to thermal emission of the day size of planets, we're now able to probe rocky planets. This is TRAPPIST-1b. And yes, these are just 2 data points, but they're really interesting data points because they're probing the temperature of the day side of TRAPPIST-1b. And that's actually really helpful to try and determine whether an atmosphere is actually present on these rocky planets, because that's not really a given. And for this particular case, it looks like the data is consistent with a bare rock. And some people are actually using this type of data, this emission spectroscopy, to compare to different mineralogies of the day side and learn more about the mineralogies of rocky exoplanets, which is really cool. And then we can also do phase curves of small planets as well. This is the example of GJ1214b. I'm actually going to come back to this later. But from this phase curve, because we're getting thermal emission at the peak of the planetary blackbody for the whole orbit, we can constrain its bond albedo, which is around sort of 0.4, 0.5, so pretty high. And we can also get a constraint on the metallicity of the atmosphere, which again is quite high. So a bit of cool stuff from small planets, but let's be honest and realistic. Small planets are challenging. We already knew that. It's okay. And we've heard about a lot of flat transmission spectra that have been measured. And there's a challenge with these spectra, not only because we're not seeing specific chemical features, but also because they're very degenerate. So if you see a flat transmission spectrum, it could be that you're seeing clouds and hazes blocking your view of the atmosphere. It could be that you have a high mean molecular weight that is sort of contracting the scale height of your atmosphere. Or if your planet is actually small enough, you might have no atmosphere at all and just a bare rock. So which one is it? I want to highlight some results from the COMPASS program that Artem mentioned yesterday. Something that I really like that they've done is that despite seeing a flat spectrum, they're actually extracting information from that, because this is not nothing. It is a flat to within a certain error bar. And even if we can't uniquely constrain the composition or the metallicity of the atmosphere, you can rule some things out, which is helpful. So this plot here is sort of the pressure in the atmosphere, where clouds or hazes may make it opaque, versus the metallicity of the atmosphere. And this flat spectrum allows you to have either really high up clouds and hazes at like less than a millibar, or a really high mean molecular weight corresponding to at least sort of 100 times solar. So you can at least exclude part of the parameter space. And this then becomes a good launching point for follow-ups of, okay, if these are the possibilities, how do we rule out high altitude clouds, or how do we rule in or out high metallicity? So going back to emission spectroscopy, I guess I already showed that I'm a little bit biased. I think it's really cool that we can measure these temperatures of the day sides of small planets. So this is now the example of TRAPPIST-1c, where this emission data point from JWST, it kind of constrains the temperature of the atmosphere at least at around 50 microns. And in this case, it's degenerate between an ultramafic rock surface, or probably some other surface compositions as well, or a sort of thin atmosphere with a bit of CO2 in it. So one way to break that degeneracy would be to observe at other wavelengths as well. But if we're talking about challenges here, something to note is that the smaller and cooler your planet is, by smaller I mean small relative to the star, the bigger your error bars is going to be. So yes, we can get a temperature, and so the flat line case, you at least have that information. But if you want that information to be useful, you want to make sure that you can get a precision which is informative for a particular scenario. Another really big challenge, which I'm going to kind of condense into one slide, is the connection between the atmosphere and interior. Let's say that you measure some water in an exoplanet atmosphere, like a sub-Neptune, for example. Cool. You could even have an abundance for it. But what does that actually mean? If you see the water, is it just from the nebula gas, and then you escape some hydrogen and helium, and you've got a high abundance of water left at the end? Maybe. Did you start off dry? Did you have a hydrogen-rich atmosphere and it reacted with the magma ocean underneath, reacted with the oxygen and the silicates and produced a lot of water? Also possible. Or did your planet form with, having accreted ices and with that additional water in that sense? Also a possibility. So if we want to understand what atmospheric constraints are telling us about the bulk composition of the planet, we really need to understand this connection between the atmosphere and interior. And there are a lot of processes to look into. Laura touched on this in her talk on Monday. Things like outgassing, dissolution, redox reactions, condensation, convection, or the inhibition thereof. I'm not going to go into full detail into all of this, but we need to take this into account when we interpret atmospheric observations. Okay, so I spent way too long making this meme last night, but what do we do next? We've seen that there are some positive stories and cool results from small planets with JWST, but also a lot of challenges. Where do we go from here? One option that we have is that for some really high-value targets, we can double down. Let's say you have a flat spectrum. You can keep observing it, beat down the error bars, and see if you actually get any spectral features maybe at some point. You could also observe that planet again, but in a different wavelength range, or in a different geometry, maybe go for a phase curve or something. So I'm going to talk about the example of GJ1214b in just a second, in that context. Another approach that we can take is to kind of put our experimental hats on and think, are there any extremes in the population that can simplify these degeneracies for us a little bit, and where the signal to noise that we can get right now actually tells us something interesting and answers a sort of useful question. So I'm going to talk about an example of lava worlds in a minute and how they can help us to learn something about volatile retention. Okay, so I'm going to speed up just a little bit, but I'm going to talk about the example of GJ1214b. This is a pretty famous sub-Neptune because, partly because it has a degenerate possibilities for its interior composition. It could, in theory, be a water, sort of volatile-rich planet, or it could be sort of rock plus hydrogen. And notably, it has very, very good observability metrics. So if you want to look for a sub-Neptune, or at least pre-JWST, you'd be like, okay, it's obvious we have to go for this planet. Its observability metrics are so good. So naturally, it was observed extensively with HST and other facilities, and it produced, I would say, lovingly, the most famous flat spectrum in exoplanet atmospheres. Yeah, but expensive. I don't know if JWST is challenging that. And so I like to think of this as a great example of where a flat spectrum was actually really useful. Because this is not just a flat line. This is a really, really flat line. It's very precise. And so what this spectrum said is that this is not just a high mean molecular weight atmosphere. To get this flat, you need to have clouds or hazes in the atmosphere. And this was sort of like the first detection of clouds or hazes in a transiting exoplanet atmosphere, which is really cool. But okay, we maybe want some compositional information now. So, and we have JWST. And so there was a JWST phase curve observed for GJ1214b in the mid-infrared, 5 to 12 microns with MIRI LRS. And so with the phase curve, you get the emission as a function of orbital phase, and you also actually get a transmission spectrum for free as well. I'm going to whiz through some of the observations that we got and how we interpreted them. So starting off with the free transmission spectrum, it's still flat in the mid-infrared, but that's again actually a really useful flatness because it's flat way out of these longer wavelengths. And this time it's kind of the other way around. Clouds and hazes are not enough to flatten this in the mid-infrared. You need a high metallicity to do that. So that tells us that this atmosphere is around like at least 300 times solar in sort of metallicity units. So that's very useful. The phase curve is telling us a very consistent picture. Based on the day-to-night temperature contrast, the best fits with the GCMs require a greater than 100 times solar metallicity in the atmosphere. So it's similar to the transmission spectrum. We also have the day-side and night-side emission spectrum. These are consistent with the transmission spectrum and the phase curve, but not hugely constraining the metallicity, but are showing potential signs of reflective hazes as well, which I won't go into detail. Feel free to ask more about that. So the other thing, which I forgot to say, is that the phase curve is constraining the bond albedo to be around 0.4, 0.5. And then we've got this sort of high metallicity constraint. So let's try and do this extrapolation exercise of going to the interior of the planet. I'm not saying this is a perfect extrapolation by any means, but let's see how it helps to have atmospheric information. And so what we did was I was modeling the atmosphere in a way that is consistent with the JWST observations. And Matt Nixon, who's a postdoc at the University of Maryland, but will be starting a 51 peg at ASU, he has modeled the interior structure of this planet and kind of coupled that to my atmospheric models to stitch them together. So, very quickly, the atmospheric models that we used are ones that are consistent with the day-side spectrum. And to do that, we find that we need a haze production rate of around 10 to the minus 11 grams per centimeter square per second. This is basically an amount of haze that gives you the right bond albedo, but doesn't cool down the day-side too much. And if we do that, we get temperature structures a little bit like this. And why do we care about the amount of haze? That's because if you have not very much haze, then your deep temperatures are a bit hotter. And if we actually have the right amount of haze, the deep atmosphere gets a bit cooler. And that means your interior is cooler and denser, and you actually need more water or other volatiles to make up for that when you model the interior structure. So if we put this all together and see what does this tell us potentially about the interior structure of GJ1214b. Here we have the mean molecular weight of the atmosphere versus the best fitting mass fractions. And I want to focus on the blue, which is the water mass fraction. Obviously, you probably should have carbon in there, as we discussed yesterday. This is just a proxy. So given that we have information from the JWST observations, the mean molecular weight that is preferred is around here, 300 times solar or higher. If we go too high, you need an ice to rock ratio, which isn't really realistic, so we're going to rule that out. That leaves this sort of narrow regime of mean molecular weights of this mixed envelope that result in a 30 to 48% water mass fraction in the planet. I don't want to fixate on these numbers because obviously models aren't perfect and there isn't carbon in this, etc. But the point that I want to make is that having the constraints on the hazes, the bond albedo, the metallicity are helping us to narrow down the parameter space of understanding the interior. Okay, in the last few minutes, I want to switch to the second case that I was talking about, which is going for some more extreme targets. And one of my favorite types of extreme targets are lava worlds, because we talked about all this degeneracy in the different atmosphere and interior connections and processes. But what if we just had the interior of a planet and it was evaporating and we could just look at the surface material coming off it? Wouldn't that be so much easier? And look, we have some lava worlds in real life where we can do this. These are a subset of the lava worlds that have JWST programs, either completed or in progress. And we can see that as a function of mass and radius, some of these are consistent with an Earth-like interior composition. So yeah, maybe like a bowl of rock, classic lava world. And some of these are a little bit under-dense. So what's going on there? Do they have something funky going on with their cores? Have they retained some volatiles? Do they have an atmosphere or global atmosphere? Well, we might be able to find out with JWST. And I want to focus on, just for a second, one of my favorite ones of these, TI561b. This is a target where we recently got the JWST data. It's not quite ready to share yet, but I'm going to tell you some of the things that I plan to do to interpret the spectrum. And this is a really interesting target because the star is a thick disk star, 10 gig years old, alpha enhanced, and the planet, yeah, is underdense. Also, the day side of this planet, if it was a bare rock, would be 3,000 Kelvin. So if it has volatiles, then it held onto them for a really long time despite really strong irradiation. And that would be a cool thing to be able to probe. So if we're asking now, like, how can we tell if these lava worlds have volatile-rich atmospheres? What we want to distinguish is either scenario A, where, let's say, it's not held onto volatiles, we just have a bare rock, maybe something interesting going on with the core, that rocky surface should evaporate under this high radiation into a sort of silicate-rich atmosphere. So we could try to look for that. And then scenario B that we want to distinguish is, well, what if the planet did hold on to some volatiles? Then the interior is this mix of silicate material and volatiles, and it's hot enough that both of those things should be evaporating at the surface. So we might expect an atmosphere that is a mixture of rock vapor and volatile constituents. So it might seem easy to just think, okay, let's point a telescope at these lava worlds and we'll definitely know if there are volatiles or not. But the observability of these features is non-trivial, as I think I demonstrated earlier on. I don't have time to go into the details of why these may or may not be observable. Feel free to ask me about the balance of optical versus infrared opacity in these atmospheres. But the TLDR of this is that, yes, there are some cases where we can detect absorption features from volatiles in the atmospheres of lava worlds. This is one case which has a fairly bright star, HD 3167b. And this is simulated data where I've put in a volatile-rich atmosphere made of water and CO2. And you can see that with 5 eclipses with near spec, which is a very reasonable amount of time to ask for, you could distinguish a sort of CO2 dip here and a combination of water and CO2 down here. I will caveat this and say this is a clear atmosphere, and I put in quite a lot of volatiles as well. So we should definitely try and observe things like this for some of the lava world targets. But what if we don't see features? Let's go back to realism again. What if the spectrum is too noisy and we can't get that? Well, let's go back to the dayside temperature again. That can be really informative. Sure, we might not be able to perfectly distinguish the constituents of the atmosphere, but in the same way that we can distinguish a hot, bare rock, we can also tell the difference between the balance of different molecules in the atmosphere, or different species in the atmosphere, that heat it up because they have a lot of UV optical opacity. For example, rock vapor does a really good job of heating up the dayside, versus other species which are better allowing the atmosphere to cool down. And of course, clouds can also cool down the atmosphere by increasing its bond albedo. So by seeing where these are models for TOI 561b, so by seeing where the data lies on this, is it hot and like a bare rock? Is it really cold, in which case there would be evidence for a volatile-rich atmosphere? We can start to probe whether this planet has an atmosphere and some information about what that atmosphere could be made of. So I'm going to wrap up now, because I think I'm almost running out of time. Hopefully I've convinced you that not all featureless spectra are bad. It's all good. But we do need to think about, what do we prioritize going forward? So in some cases, if we do have high-value targets that probe interesting parts of parameter space or are particularly observable, it can be helpful to double down and just try to characterize them in as much detail as possible and see what comes out, like the case of GJ 1214b, and this is kind of happening with the TRAPPIST planets as well. But also, I think it's really useful to think about these extreme end members, where we can probe parts of the processes that we're interested in and maybe leave out some of the ones that complicate stuff. For example, lava worlds where we have the surface evaporating directly into the atmosphere that we're observing. And just to finish now with a question for all of you, since we have lots of formation people and diff people in the room, I'm really curious to hear about what extremes and sort of interesting scenarios you would be interested in probing in terms of the atmosphere. This week I've had discussions with some of you about binary systems, for example, young planets. Lava worlds are another one. We're about to hear about a sort of disintegrating planet from Nick later on. So if there are any other areas of parameter space that you think we should be probing, I would love to chat. And I will leave it there.
Thank you for staying on time. We'll start the question from this side, and then we go alternatively.
Hello, Arturo Ceballos from Univ. Excellent talk. I was really invested into everything. It's very, very nice. At least for me, it's great to finally be able to characterize planets. I just wanted to ask. I think it's just more opinion based. Wouldn't then G-yacht 1214b rather than a mini Neptune, sub Neptune, have a more fitting name to be a super Venus. As in, I would expect for a planet with this type of atmosphere to be mostly steam, right? And the temperatures inside have to be quite extreme due to the greenhouse effect. And I don't know if that's considered in these atmospheric models, like the consequences of them and then the chemistry that would happen inside.
Yeah, so yeah, for GJ1214b, in terms of the composition of the atmosphere, apart from the high metallicity, yeah, we don't have a super great handle on like carbon versus oxygen and stuff like that. But yeah, I mean, I totally agree that like the way that we name planets is a bit arbitrary, but we just sort of pick something. But you're right, that towards the higher metallicity end of things, then if we think of sub-Neptunes as being like really hydrogen, helium dominated, if you then have a super high metallicity and is not so much hydrogen, helium dominated, sure, thinking about it as a super Venus might be a cool thing to call it.
I propose this name.
Noted.
Thank you.
Jack, please.
Just to point out, super Venuses, Venus has very, very little water or other forms of hydrogen, extremely small. My question for you is regarding the models of GJ1214b, and there are possibilities that the interior has the rock and water substantially mixed or largely core. And what can you say about that, or how does that, is that a large source of the uncertainty in terms of the water mass fraction of the planet, et cetera?
Yeah, great question. So in this particular interior structure model, we're assuming that the envelope is well mixed, so like the hydrogen and the water in this case, but that it's separate from the mantle. But you're absolutely right that you could get like water rock miscibility as well. I think this is something that we need to include more. And also from an experimental point of view, getting a better handle of what those equations of state look like across a diverse parameter space of composition as well. For example, if we have a bunch of carbon in there as well, like how does that change the equations of state too? So yeah, that is absolutely a source of uncertainty.
Ralph Budritz, for these beautiful data you have with the rock vapor, you now can understand the composition, the refractory materials of the planet. So going back to the first day, if you know exactly the stellar spectrum for the refractories, can you now make a sensible model for at least that material in the center of these planets?
Yeah, that's something that's commonly done, where you can look at the silicon to iron ratio for the star and then apply that in the interior structure models. I guess for M-DORS it's a bit trickier sometimes to have the stellar abundances, but the typical assumption and what we assume for GJ1214b is an Earth-like ratio of the iron core to the silicate mantle. I don't know if that answers your question.
Yeah, so then it's really only the water fraction that becomes the thing that you can fix by this, right?
Yeah. Then it helps to narrow down some of that parameter space, yeah, if you lock the iron to silicate ratio. Yeah, so it helps to reduce that degeneracy a little bit.
Lauren Weiss, University of Notre Dame. I'd like to respond to your open question by proposing super puffs as a really fun extreme. They should have really like large scale heights and low mean molecular weight atmospheres. And then I know Peter Gao showed like at least one flat spectrum of one. What can you tell us about the super puff atmospheres and what they're made of?
Short answer is I don't know. It's really confusing. So, I mean, one thing that Peter proposed, right, is that they might look really puffy if you have super high altitude hazes that make the radius look really big. Because there's a point where if it's that low density, you're kind of thinking, well, how is it holding on to this atmosphere? And the hazy scenario is consistent with this flat spectrum, right? So that is one option. For some cases, I know one of the theories, I don't think this would apply to all the super puffs, but planetary rings theory, maybe for some of them. And I know in some cases, I think Kepler 51, I think the TTVs have been revised as well, and some of the mass measurements have shifted a little bit. So I think there's one which isn't flat, and like the mass shifted. But yeah, I totally agree. Really interesting population, and would love to chat more about that.
Eve Lee, pardon me, Eve Lee, UC San Diego. I have a really naive question, but I always got very confused, so I hope you can help me understand this better. Like I very often see that when you have limited dynamic range in the wavelengths, and with the flat spectra, then there is this degeneracy, as you have shown, just very high altitude clouds for a wide range of metallicity versus like just really high metallicity atmosphere. But I thought you needed metallic species like condensates to form the clouds anyway. So in terms of just cloud formation physics itself, like what we see for like cloud seeding techniques, for example, on Earth, is there some sort of a limit that you can place on the lower limit of the metallicity?
So in that case, I guess you could still, if we think of like clouds in giant planet atmospheres, like you could still get the clouds and like photochemical hazes, even if you have like a not super high metallicity in your atmosphere, if that makes sense. So it's, I think, not super constraining. You need some metals, but it would maybe, I think even in a one-time solar atmosphere, you could probably get some clouds and hazes. You could probably, like, depending on, if you get a really good constraint on like how thick you need the hazes to be, then you could do like more detailed modeling of the formation of those clouds and hazes and how much of that material you need. But I think it wouldn't be super constraining on the whole, if that makes sense.
Okay, thank you.
Bennett Skinner, McMaster University. You showed that you have these degeneracies between different models of the atmosphere for the planets, and one of the proposed ways to try to move past that is to just really narrow down the error bars on that one planet to try to differentiate between the two. I'm wondering, alternatively, would it be useful to just look at a bunch of planets, and for each individual planet, you have not broken the degeneracy, but could you, on a statistical population level, try to determine which type is more common?
That's a really good point. I think it depends on the question that you're asking. So one thing that has been looked at a little bit, I think we still need more data to fill it out, is like the prevalence of flat spectra / hazes, if you interpret it to be that, as a function of the temperature of the planet. And so you get this kind of U-shape where there's a sweet spot of where we think hazes form more preferentially, and you get a lot of flat spectra. That still has a degeneracy, obviously, with the metal content of the atmosphere. But yeah, I think we can certainly go in that direction. That's really useful, but it's good for some of those planets within that sample to go deeper so that you can just check, like, okay, is this actually haze, or is it this one actually high metallicity, and maybe that would throw the trend, if that makes sense.
Thank you.
Hi, Richard Nelson, Queen Mary, University of London. Thanks for a great talk, very interesting. I'd just like to push you on this interpretation of 40%, roughly speaking, of bulk water content, and you'll understand why I'm interested in this. So, you know, on a scale of 1 to 100, how certain are you about that number? And, you know, perhaps I can turn that on its head. What's the chances that it could just be rocky interior with a hydrogen-helium dominated atmosphere on top? What would you say, you know, roughly speaking there?
Great question. I really like the second phrasing of it, because the information that we're getting from the atmosphere is that because it has a high mean molecular weight, we have a bunch of metals in the atmosphere. It's at a temperature where, you know, we're not expecting that metallicity to get lower, deeper down in the atmosphere, put it that way.
No, sure.
So that tells us that we can't have a mean molecular weight of 2 somewhere that's balancing out a rocky interior. So to come back to the specific numbers, I'm not attached to those specific water mass fractions specifically, because there are lots of things in the model that we would want to update and make better. And this kind of applies to 2I270D as well. If you have this really high metallicity, it's telling us that we can't have like the onion structure of like just hydrogen on rock. We need some of that volatile material in there to still explain the mass and radius, and that's where that constraint is coming from.
So final follow-up point, are you saying this formed beyond the ice line?
Can I spin that round and ask everyone else?
Well, those ratios, 40%, is pretty much what comes out of your expectation about the abundance of water.
If it really has that amount of volatiles, like maybe.
Yeah.
But I would love to understand better the caveats to that and how, like, if there are any ways of doing that without falling beyond the ice line that we should be like aware of and
That'd
trying
be very
to,
difficult, I think,
yeah,
given those masses.
Yeah,
Okay.
yeah, so maybe.
Thank you very much.
Hi, Anjali. Great talk, great talk. Laura Schaefer, Stanford University. I love the silicate vapor atmospheres, obviously. I recall that Roxana Lupu was working on this, and especially working on trying to calculate better opacities for these kinds of atmospheres. And with the opacities that she was finding, she gets like huge temperature inversions, like in the upper atmosphere. So upper atmosphere is super duper hot. So I was wondering, what's the state? How well do you trust the opacities for these kinds of atmospheres? Do you include those temperature inversions in your models? Can we detect those?
Thank you for asking that. This is like my favorite question. Let me go. Okay, so this is something I had to cut out, so thanks for asking. Basically, we really care about the UV optical opacity versus infrared because exactly if you have a lot of UV optical opacity from your rock vapor, for example, it drives really strong thermal inversions. And then in the rock vapor case, yes, so to answer your question, we're including basically modeling what is being outgassed with vapor rock in this case, and taking all the cross sections that we can get from exomol and hydran and putting those in. And so we get lots of UV optical from SiO, MgO, potassium, sodium, etc. What I found is that if I try to reproduce some spectra, that don't include all of these molecules, but mostly focus on the ones that are the most dominant in abundance, so actually leaving out MgO, then I get a super, super, super strong thermal inversion. If I include MgO, this infrared opacity bump actually reduces the strength of the thermal inversion and makes it trickier to detect silicate features in the purely rocky atmosphere, rock vapor atmosphere. So I kind of wish it was more thermally inverted in a way because it would improve the observability. And then if you add volatiles, that adds even more infrared and reduces you down to sort of an isothermal atmosphere and then eventually non-inverted. If I go to the next one. So the pure rock vapor case would be like the darkest blue color. And there you do see some emission bumps from the silicates, but they're kind of small because this thermal inversion is there, but it's not like super, super strong because of the MgO specifically. And then if you add more volatiles, initially you get kind of a featureless spectrum because they add more infrared opacity, but if you have enough in the volatiles, you switch to the non-inverted temperature profile and you can get the bigger absorption features.
Okay, so really quick follow-up. Have you considered...
All right, for the interest of time, can I please ask we put the discussion of the offline, and please let's thank Anjali again for a wonderful talk.